Good morning. Today I'm going to talk about chemical equilibrium. Chemical equilibrium is defined as a state in which the rate of forward reaction equals the rate of backward reaction. In other words, there is no net change in concentration of reactants and products. This kind of equilibrium is also called dynamic equilibrium. Dynamic equilibrium is useful in predicting whether the forward of reverse reaction is spontaneous or non-spontaneous. To explain how this works, three quantities must be introduced. The first one is equilibrium constant. Equilibrium constant, it is the ratio of concentration of the products over the reactants. The first one is the equilibrium constant. Equilibrium constant is the ratio of concentration of the products over the reactants. The second one is the reaction quotient. This measures the relative amounts of products and reactants present during the reaction at a particular point in time. It aids in figuring out the direction a reaction is likely to proceed, given either the pressure of the concentration of the reactants and the products. The reaction quotient is given by the same equation as the equilibrium constant, but its value will fluctuate as the system reacts, whereas the equilibrium constant is based on equilibrium concentrations. The next one is Gibbs free energy. The road to equilibrium is down the Gibbs energy hill. This means that the total Gibbs energy of a mixture of reactants and products goes through a minimum value as the composition changes. Then all net change will cease. Then the reaction system will be in a state of chemical equilibrium. Gibbs free energy is used in chemistry to help determine end product ahead of time, whether a chemical process is spontaneous or non-spontaneous. In a spontaneous energy, it happens automatically. You might have to start off the process with a little activation energy, then the rest will take care of itself. A good example is combustion, the burning of substances to produce heat and energy. You may have to light the substance first, giving it activation energy, but once the substance burns, it continues by itself. In a non-spontaneous process, a continuous energy input is necessary for the reaction to proceed in a certain direction. A good example is photosynthesis, a process in which plants use to make glucose. Photosynthesis requires energy in the form of sunlight to drive chemical reactions. Therefore, at night, when it's dark, photosynthesis does not work. Gibbs energy, denoted as G, is equal to the sum of enthalpy plus the product of the temperature and entropy of the system. So what are the factors that affect chemical equilibrium? These are Le Chatelier's principle and catalysts. Le Chatelier's principle states that the changes in temperature, pressure, volume, and concentration of a system will result in predictable and opposing changes in the system in order to achieve a new equilibrium state. Le Chatelier's principle states that if a constraint is applied to a system in equilibrium, the equilibrium will shift as to tend to counteract the effect of the constraint. So what is an example of the Le Chatelier's principle? The opposite effect occurs for endothermic reactions, which are shifted to the right by rising temperature. The classic example of practical use of Le Chatelier's principle is the Haber-Bosch process for the synthesis of ammonia, in which balance between low temperature and high pressure must be found. So how does temperature affect Le Chatelier's principle? For instance, if you raise the temperature on the endothermic reaction, it is essentially like adding more reactants to the system. Therefore, by Le Chatelier's principle, the equilibrium will shift to the right. Conversely, lowering the temperature on the endothermic reaction will shift the equilibrium to the left, since lowering the temperature in this case is equivalent to removing a reactant. A change in pressure or volume will result in an attempt to restore equilibrium by creating more or less moles of gas. For example, if the pressure in a system increases or the volume decreases, the equilibrium will shift to favor of the side of the reaction that involves fewer moles of gas. Similarly, if the volume of a system increases or the pressure decreases, the production of additional moles of gas will be favored. According to Le Chatelier's principle, adding additional reactant to a system will shift the equilibrium to the right, towards the side of the products. By some logic, reducing the concentration of any product will also shift their equilibrium to the right. I'm going to discuss the effects of catalysts on equilibrium. Recall that catalysts are compounds that accelerate the progress of a reaction without being consumed. Catalysts allow the reaction to proceed faster through a lower energy transmission state. By lowering the energy of the transmission state, which is the rate of limiting step, catalysts reduce the required energy of activation to allow a reaction to proceed, and in the case of a reversible reaction, reach equilibrium more rapidly.